Hi there, my name is Bill Tomlinson. I'm a professor in the Department of Informatics at the University of California, Irvine. When Dr. Toland invited me to give a guest lecture for your course, I was excited to accept. I was a professor in the School of Information Management at Victoria from 2017 to 2018, and I remain an adjunct professor with SIM. I'm also a researcher studying sustainability in computing, so both the topics of this course and also the Victoria community itself are near and dear to my heart. So I'm based here in California, and there are two items I'd like to bring up about my local context. First, there's been an increasing number of forest fires in California in recent years. These forest fires are an unsettling manifestation of global climate change. Second, the US is still in the thick of the COVID pandemic. New Zealand has done a much better job of managing the virus than the US has. COVID, too, is a manifestation of humanity's lack of sustainability as we encroach on wild spaces. Both of these issues point us towards the topic I'll be talking about today, computing within limits. Computing within limits is a new computing subfield that explores ways that new forms of computing can support well-being while enabling human civilizations to live within global ecological and material limits. Now, this term applies to both the research community and one particular academic article that we published. So before I get into the content of the article itself, I'd like to give you a bit of backstory about how my colleagues and I started studying it. So I've been working on sustainability in computing since around 2004, and in 2009 I had a PhD student named Six Silverman, and he and I wrote a paper called Post-Apocalyptic Computing, looking at the role of computing in a variety of different possible apocalyptic scenarios. Around that same time I had a kid, and suddenly sustainability became a much more serious concern, as I felt like I wasn't just looking out for myself, I was looking out for my family and this small child that was on my chest. And so over the next few years, I began talking with various different colleagues, some in my own department like Bonnie Nardi and Don Patterson and Deborah Richardson, and some from other places. So Bharath Raghavan, who was working at a research lab associated with UC Berkeley, got in touch with us. And Daniel Pargman, a scholar from Sweden, came to visit us on sabbatical. And Birgit Penzestadler came to be a postdoc with us. She was coming from Germany. And later we started talking with Jay Chen as well, who is one of Bharath's close collaborators. And Jay is at NYU Abu Dhabi. And together we started the Computing Within Limits workshop. And it's now in its 6th year. And a couple of years ago, in 2018, we decided we'd learn enough to write a broad article about the core themes of this community. And so that's the article I'll be telling you about today. The reason I wanted to tell you this backstory is because I feel like it's important to note that scholarly research is made by people. And I once had a similar realization about computers. The fact that Google or Microsoft Word or the internet works isn't just magic, it's because people wrote a bunch of code to make it that way. And similarly, if a program crashes, it's not just the randomness of the universe, it's because some programmer didn't test their code well enough or was having a bad day when they were writing that particular piece of software. Similarly, science and academic research are also made by people. And often, they're people who've been working hard on a given topic and know more about it than most people, but still, they're just regular old people, and sometimes they're wrong. And so that's something that's useful to keep in mind as you learn about various different scholarly findings. So now that you have the backstory, I'd like to talk to you about the content of the Computing Within Limits article itself. So people who build computing systems are often seen as inventing the future. And the fact that I'm able to give this guest lecture thousands of miles away and send it to you all is a pretty neat example of the kind of innovations that computing enables. But the futures that computing people build for, the futures that they design for, are often very much like the present, only more so. So most computing work is premised on industrial civilization's default worldview in which ongoing economic growth is both achievable and desirable. And so this builds on things like Moore's law, the idea that there has been for the last few decades, basically exponential growth in computing power over time. However, researchers in other fields are identifying challenges with how the industrial world is presently operating. So the industrial world currently has a strong focus on extraction, the idea of taking things out of the world to make whatever stuff people are willing to buy. And much of industrial civilization's apparent success relies on the idea of sacrifice zones, that there are areas of the world that can be treated as disposable, and that the people and the other organisms that live there are also seen as disposable in that mental model. And so this growth-focused worldview is at odds with other scientific fields which see growth as deeply problematic for ecological and social reasons. Ultimately, growth can't continue forever. There are limits on how much growth can happen. There are many different types of limits. There are limits on the amount of waste that Earth can absorb. So CO2 is the most prominent of these, the sort of human waste products, but there are lots of other ones in terms of air pollution and water pollution and other kinds of waste. There are potentially limits on the availability of energy. So there's an idea called peak oil that we either have passed or are soon approaching the point at which we will no longer be able to extract. There will be dwindling supplies of oil, and the idea of peak oil is also juxtaposed with the idea that if we burn all of the oil that we have access to, it will be hugely problematic for climate change reasons as well. But these limits also point to the possibility of peak information, the idea that there may come a time where we no longer have access to effectively infinitely growing amounts of access to information. Right now, when I buy a new laptop, I can essentially package up my old laptop and stick it in the back corner of my hard drive so I always have access to that information. However, if we don't continue to have increasing innovation, according to Moore's law, if limitations on resources and other limits that we are currently starting to face limit our ability to have growing amounts of information, we may need to start focusing on how do you cull that information, how do you decide what bits of information are important to keep, rather than being allowed to simply keep track of the vast majority of information we have access to. So there's an archaeologist named Joseph Tainter whose work has been foundational to our thinking about this topic. He wrote a book in 1990 called The Collapse of Complex Societies that argued that most civilizations eventually collapse, and they typically decline over a period of decades or centuries. Tainter presented collapse as a process that arises from increasing social complexity that, over time, creates burdens for systems that those systems can then eventually not sustain. Various different scholars in different fields have proposed ways to avoid the runaway growth that industrial civilizations are currently pursuing. So Herman Daly proposed that we should pursue a steady state economy that would maintain material throughput at a constant rate. And there's been a group of economists, mostly based out of Europe, that have been exploring the possibility of degrowth, an approach that prioritizes social and ecological well-being over excess consumption and overproduction. So what we've been trying to do is to study the role of computing in all of this. And so we've proposed that the computing field should transition toward a viewpoint of computing within limits and try to explore ways that new forms of computing can support well-being while enabling human civilizations to live within global ecological and material limits. And we've come up with a number of different principles that we think should underlie this change in approach. And I wanted to tell you about the three main principles we came up with. The first is that people should interrogate whether the work that they're doing is primarily serving to enable economic growth or not. And this applies everywhere from what project you're working on right now all the way up to what career you choose to pursue. There are some careers that are inextricably linked with economic growth and others that aren't necessarily so and can provide other services to human society and to other organisms. The second principle is to envision futures of scarcity and what systems might be relevant in those futures of scarcity. So, what will the world be like when there are 140 million climate migrants, as the World Bank predicts? What will the world be like when 2/3 of all countries are in sustained economic contraction rather than growth, as researchers from Berkeley and Stanford predicted in a paper in Nature in 2015? And the third principle we proposed is thinking about how to reduce your long-term energy use and material consumption in all of your work. And here the term long-term is critically important. Ultimately, this is all a long game. Plan for 10 or 20 or 50 years, not next month or next quarter. So to give a concrete example, I wanted to talk about another paper that we just published. And this is an article about giving the environment some control over corporations. So in many legal frameworks around the world, corporate directors are selected by shareholders. And there's proposed legislation in the US right now that's seeking to enable employees to have representation on corporate boards as well. Nevertheless, current approaches to corporate board selection could result in the systematic discounting of other unrepresented stakeholder groups beyond shareholders and employees, for example, the environment. So to investigate this issue, we envisioned a new kind of corporate director beyond shareholder-selected directors and employee-selected directors. We proposed the idea of environment-selected directors. So we then created an online simulation and conducted some experiments with that simulation where human participants were assigned to act as corporate directors, with some being told they were shareholder-selected, some being told they were employee-selected, and others being told they were selected via a vote by a committee of scientists who study the local and global environment in question. And the results from this study found that participants assigned as environment-selected directors exhibited more balanced preferences across different stakeholder groups, and this was behavior that was significantly different from both shareholder-selected and employee-selected directors. The results from this study suggest that it may be useful for future legislation to consider including this novel form of director, the environment-selected director, on corporate boards, as well as shareholder-selected and employee-selected directors. And so this article is an instance of computing within limits because it pushes back against economic growth. Having stock prices go up, essentially having shareholders' bank accounts grow, is a key factor, or is a key focus of current corporations. By giving the environment some control over how corporations act, this approach could help corporations support the long-term best interests of both humanity and other species as well, as opposed to just shareholders. And this project used innovations in simulation and crowdsourcing to try to explore how to enact these kinds of societal change. So, to wrap up, computing is critical both to the operation of how infrastructures of global society operate, and also to the ways that people think about and design for how these futures could unfold. So how those computer systems are built and how they work will be critical in shaping a society that meaningfully adapts to global limits. And I'd also like to note that you all are well positioned to be leaders in this field and related fields. You are clearly smart because you got into Victoria, you're well educated, you're positioned as leaders by being part of the global intellectual community. And I'd like to ask you, as I close, to take that opportunity to go make the world a better place and do what you can, not just necessarily to make money, but also to try to see how you can support human well-being and the well-being of non-human species as well. Thank you all for your time. I hope you have a good day. Bye-bye.